Welcome to this session. This session, we are going to show that the set of all polynomials over field F is a vector space over the same field F. So let's run through the proof. So first, let's F, G, and H be polynomials in this set such that f of x is given by a0 plus a1x plus a2 x squared plus a3 x cubed up to plus an x power n plus other several terms of the same pattern. G of x to be given by b0 plus b1x plus b2 x squared plus b3 x cubed up to plus bn x power n plus other terms, and h of x to be given by c0 plus c1 x plus c2 x squared plus c3 x power 3 plus other several terms, cn x power n plus other several terms of the same pattern. And so because there's a pattern here, we can write this in condensed form as summation of all ai's x's power I. So I running from 0 to infinity. This one, we can write it as summation I b sub I x power I. And then this one, we can write it as summation I c sub I x power I. So this is just the short form of writing these polynomials f, g, and h. And then let alpha and beta be any two elements in the field F, and be the addition operation and scalar multiplication respectively. On this set, we write this one as square brackets. So I've given the base of our proof structure. So let's scan through the 10 axioms of our vector space. So the first one is to test closure. Does closure with respect to addition holds in this set F? So let f and g, their functions in this set of polynomials. Then we have f plus g will be given by of x, the same as f of x plus g of x, which is the same as summation ai xi plus summation bi xi from the way we have defined f and g. So we can always put these summations together. So summation of ai xi plus bi xi, and this is the same as summation ai plus bi, and then xi. And you see, this should be clear that this is the structure of all the elements or all the vectors in this set of polynomials, because this answer has the same structure as polynomials whose coefficients are real numbers. So this can be fixed to be, say, one number, say ki xi, and that's the structure of all the vectors of this within this set of polynomials. So this is just another polynomial in this same set F. So therefore, closure holds. And then number two, we have to prove commutativity. So let F and G be two polynomials in this set. Then F plus G, the same as F of X plus G of X, which is the same as summation of all ai x power I plus summation bi x power I. And then because we have summation of elements of the same format, then we can write it as one summation. And then we say ai xi plus bi xi. And then this is the same as writing summation ai plus bi and then xi. But you see, this can be written as summation bi plus ai and then times xi. This is because AIs and BIs are elements in the field which obeys commutativity property in the field F. So this we say by commutativity of assembly by commutativity on F. So therefore, summation F, or really the function F of X, so from this one, we can write this one as summation bi xi plus summation ai xi, and this is the definition of f of x, and this is the definition of g of x, and this is the definition of f of x. So remember we had f plus g so i.e. f plus g is the same as g plus f, and this is to mean that f plus g is equals to g plus f. Therefore, commutativity on this set of polynomials holds. Next, associativity. So f plus g plus h equals to f of x plus g, this by definition, which is the same as f of x plus g of x plus h of x. And we know we have defined this one as summation ai xi plus, this is summation bi xi plus summation ci xi and so because these are just real numbers, or these are just elements in the field f, then we can write this one as summation ai xi plus summation I bi xi, and then plus summation I ci xi. So this is because we are saying by associativity of addition in F, or you can say on F. So the next thing, this is the same as writing summation I, so ai xi plus bi xi, and then plus summation I ci xi. So this is the same as writing summation I ai plus bi xi plus summation ci xi. So this is the same as f plus g, and then plus, this is the definition of h. Remember, these are in terms of x, and we started from f plus g plus h of x. So which tells us that f plus g plus h is equals to f plus g, and then plus h. So that shows that associativity holds. And then number 4, additive identity. Now, let this be given by summation since 0 is an element in the field F. Now, when you say f of x plus this 0 will have summation of i's ai xi plus summation of all i's zero xi, and this is the same as summation ai plus 0 xi. And you see, this is the same as summation of ai xi. Reason as to why you're saying that one is because 0 is, I can just say, since additive identity exists in F. So ai plus 0 just the same as ai. So that's why they have this. And this is not different from the definition of f of x. So additive identity in this set exists. Number 5, additive inverse. Does additive inverse exist? Now, let F be in this set, then minus F is also in that set, such that if I say f of x plus minus f of x, this will give me summation ai xi plus summation. Now remember, negative f of x is the same as summation I of negative ai xi. So I'll have negative ai x power I of I, which will give me summation ai plus minus ai, then I multiply everything by x power I, and this will give me 0 xi. So f of x plus minus f of x is giving me this. And from what you have done previously, this is just the 0 polynomial. So it is indeed confirming that an additive inverse exists in the set F. So additive inverse exists in F. Scalar multiplication so if I pick alpha multiplied by f of x, I'll have alpha summation ai xi, and then properties of real numbers. This summation can be written as properties of elements in F, alpha ai xi which is actually an element in this set F, or this is just a constant. So multiplying by coefficients of xi doesn't change the structure of the polynomial. So therefore, closure with respect to scalar multiplication holds. Number 7, distributivity. So we start by left distributivity of multiplication over addition. So we have alpha f of x plus g of x will be given by alpha into summation ai xi plus summation bi xi, and then this is the same as alpha summation ai xi plus alpha summation bi xi. And you see by definition, this is alpha, this is the structure of f of x, and this is the structure of g of x. So i.e. alpha into f of x plus g of x is giving us this one. It's the same thing as saying alpha into f plus g is equals to alpha f plus alpha g. So therefore, distributivity or the left distributivity of multiplication of addition holds. Number 8, right distributivity. Now, if I pick alpha plus beta, which are in the field F, I multiply by a polynomial f of x, then do the same thing as saying alpha beta summation ai xi. This being a constant, just multiply by this coefficient. So we have summation a summation of ai xi plus this beta summation ai xi. But you say this will be a, this alpha, not a. Alpha, this is f of x plus beta, this is f of x. So alpha beta times f of x is giving us alpha f of x plus beta f of x, i.e. alpha plus beta times f is nothing but alpha f plus beta f. And this is the structure of the right distributivity property. So therefore, distributivity holds on F. Second last one, number 9, associativity with respect to scalar multiplication. So if we have alpha, beta, we multiply by the polynomial f of x, then this is the same thing as writing alpha, beta, summation, ai, xi. And then I can write this one as alpha, then I bring in the beta, and then ai, xi. And so this is the same as writing alpha, summation, beta, ai, xi, which is the same thing as writing alpha into, now I put beta outside, and then ai, xi. And you see this summation is what defines f of x. So alpha, beta, f of x is equals to alpha, and then this is the beta, f of x, i.e. that if I take alpha, beta, I multiply by f, I get alpha, and then beta times f. So associativity holds. And lastly, identity multiplication. So 1 is an element in the field f. So when I take 1, I multiply by f of x, I have 1 times ai, xi, and then this is the same thing as saying 1 or summation, I bring in the 1 times ai, xi. But remember, 1 is a normal unity in f, and then when you multiply unity by any element in f, then you get the same element. So this is the same as summation. 1 times ai is ai, xi. So remember this 1 times f of x. And you see this is the definition of f of x. So 1 times f of x equals to f of x. And that is what it's supposed to be. So therefore, since, I'll just say, since all the 10 axioms are satisfied, all the properties of a vector space are satisfied, then f It's a vector space. That's how we solve that problem. Thank you.